Hi children, in our last session we have seen current carrying coil behaves like a magnet and the field lines around the current carrying coil we have discussed, and also the factors depending on the strength of magnetic field around a coil. That also we have discussed. What are the two factors we discussed? Yes, the intensity of electric current and the number of turns of the coil. These are the two factors on which the strength of a magnetic field around a current carrying coil depends. Now let us consider, here you can see a spring shape is given, isn't it? A wire wound in the shape of a helix. This shape is known as helix, just like a spring. So a wire, an insulated wire wound in the shape of a helix. This is known as a solenoid. So a solenoid is an insulated wire wound in the shape of a helix. Such coiled conductors are usually used to make use of magnetic effect of electric current. So here you can see in this coil both the ends can be connected to the battery and current will be passed through it. If the current passes, this coil behaves like a magnet, and this coil, the magnetic field around this solenoid just resembles just like a magnetic field lines of a bar magnet. The magnetic field lines around a current carrying solenoid resembles like the magnetic field lines around a bar magnet. So one end will behave like a north pole and the other end will behave like a south pole. So a solenoid has both ends, north and south pole, and one end will be north pole and the other end behaves like a south pole of this magnet. And how to identify, how to recognize the polarity of this solenoid? Okay, so polarity of the current carrying solenoid can be identified or recognized by simple method. See here, you can write an S on your notebook. Okay, and write an S, and we can complete this S as a circle if we move from here this side to this side, isn't it? In the clockwise direction. If we move in the clockwise direction, that S can be completed as a circle. So this clockwise motion, you can see the clockwise, the current, if the current flows in the clockwise, this represents the direction of current. Okay, yes, the letter S can be represented as the direction of current. So this direction of current is clockwise when we complete the circle by writing S. Then this clockwise direction of the current. If the current flows in the clockwise direction, that represents the south pole. Okay, if the current passes through the solenoid or the end of the solenoid at which the current passes in the clockwise direction, that end is south pole of the solenoid. And you see the N here, the N is written here. By using this letter N, this written N, here we can complete the circle as if we move in this direction, or you can remove this from here to here in the anti-clockwise direction. So as if the end of the solenoid which represent the end of the solenoid through which the current flows in the anti-clockwise direction is the north pole of the solenoid. Okay, so south pole means the end of the solenoid through which the current flows in the clockwise direction, then that end is the south pole of the solenoid. And if the current flows in the anti-clockwise direction from the end, if we view from the end and the current flows in the anti-clockwise direction, then that end will represent the north pole of the solenoid. Okay, and now here solenoid behaves like a magnet. The magnetic field lines of a solenoid resembles like the magnetic field lines of a bar magnet. The end, if the end at which the current flows in the clockwise direction is the south pole, and the end through which the current flows in the anti-clockwise direction, then it is the north pole of the solenoid. Now, what are the factors on which the strength of the, can we increase or decrease the strength of the solenoid, magnetic field around the solenoid? Yes, we can increase and the strength of the magnetic field around the solenoid by increasing the number of turns and also by increasing the intensity of current. And one more thing, if we insert a soft iron piece inside this solenoid, insert a soft iron piece inside this solenoid, then also the magnetic strength of magnetic field increases. Okay, and that soft iron piece which is inserted within the solenoid is known as core of the solenoid, core, C-O-R-E, core. So if we insert a soft iron core inside the solenoid, that also increase the strength of the solenoid, sorry, magnetic field, increase the strength of the magnetic field around this solenoid. And again one more thing, the thickness of that soft iron core also one of the factor of showing the strength of the magnetic field around this solenoid. So, area of cross section of the soft iron core, intensity of electric current, number of turns of the solenoid, and soft iron core. The nature of the core material used. Okay, these are the factors on which the strength of solenoid magnetic field around a solenoid depends. Once again, the strength of magnetic field around a solenoid depends upon the number of turns of the solenoid. The second one, the intensity of current passing through the solenoid. Third one, the core material, nature of the core material used in the solenoid, and the fourth one is the area of cross section of the core material, area of cross section of the core material. Okay, these are the factors on which strength of magnetic field depends. So here you can write it as, based on the above activities, tabulate the factors affecting the strength of magnetic field of a solenoid current carrying current. So what all the factors you can write? Intensity of electric current you can write, then number of turns of the solenoid you can write, then nature of the core material you can write, and the last one you can write the thickness or the area of cross section of the core material used. That are the factors. Now you can see the picture here. Here is the picture of a bar magnet, north and south pole. Around it, from north pole, the magnetic field line starts and enter into the south pole. And here in the case of solenoid also, you can see the same, the magnetic field lines resembles as the bar, that of bar magnet. Okay, and here from the picture you can identify that here it is outside, is an outward arrow is outward direction. This represents north pole, and the enter into the south pole. This enter south pole, or otherwise I told you south S and N. Here you can see the positive terminal is connected here. That this is the direction of current. If you view from this side of the solenoid, the current is in the anti-clockwise direction here, anti-clockwise direction. So this side is north, and here the current flows this end. If you view, the current flows in the clockwise direction. So this is called the south pole of the solenoid. Now, what are the difference between this bar magnet and a solenoid? I told you the solenoid is a coil, isn't it, wound in the shape of helix, and here this will behave like a magnet till the current flows through it. If the current flowing through this solenoid is stopped, as soon as the current stops, this magnetic property will also loses. And the current carrying solenoid can retain its magnetic property till the current flows through it. As soon as the current stops, it loses its magnetic property. So this type of magnets are temporary magnet, and this type of magnets are called electromagnets. So what is an electromagnet? It is a magnet which in which the magnetic property is gained by passing electric current through it. Okay, the magnetism is gained by passing electric current through the solenoid. And such type of a solenoid is a temporary magnet, okay, or it is an electromagnet, and the electromagnets are temporary magnets, and this bar magnet is a permanent magnet. And another one, if we change the direction of the current here, the current here negative and this end positive, the current passes in the opposite direction. As soon as then what will happen? The poles interchanges. In this case, it is north and here south. If we reverse the current, then this will become north and the other will become south. So the poles of the electromagnet can be changed by changing the direction of current. Okay, and the poles of bar magnet cannot be changed. It is permanent. Bar magnets are permanent magnets, and electromagnets are temporary magnets. The poles of bar magnet cannot be changed, and the poles of electromagnets can be changed by changing the direction of current. And then what is the next one? These are this bar magnets or natural magnets. These are natural magnets. Bar magnets are weak magnets, but solenoid or electromagnets are strong magnets. Okay, children, I hope all of you understood this much, and in the next we will continue in the next session. Till then, bye.